Okay, hi everyone. So let's talk briefly about friction. You'll talk about more when you get back from summer. But you do need to know what this is in order to answer the questions. And we want you to start friction straight away. So what is the formula for friction? It's known as F in italics or F with subscript R. And we'd call that equal to mu R, where R is the normal reaction between the particle and the surface. And mu is what's called the coefficient of friction. Now, essentially, what mu is it describes a relationship. It gives a kind of quantity, a proportion, a fixed constant between two particles interacting with each other. So that can be a particle and a surface, or two surfaces interacting with each other. And that mu would be an indication of how rough those two surfaces are when they pass it over each other. Now, in general, so if mu is 0, that must mean that those surfaces are smooth, okay? And if you get a negative mu, then that means your friction's in the wrong direction, right? Or you've definitely made some kind of error. So you've either in the wrong direction, or maybe you resolved it wrong or something, but that should be a warning sign. And generally mu is going to be between 0 and 1. And if you do get it really close to 1, or 1 itself, that's so unusual. And that should make you think, maybe I've made a mistake here, because normally mu wouldn't be anywhere near 1. It would actually be quite a bit lower than that. Okay, so if you're getting anything above 1, again, that's warning signs that something must be wrong in a general question. Now, I have put equals to here, but actually friction, that's not technically true. So at the moment, this is F max, okay, because F max is mu R, but friction itself is actually equivalent to less than or equal to mu R. And the reason for that is, if you think about, you have a particle on a table or something like that, okay, and let's say this is a rough surface, so you're looking for the word rough. As soon as you hear rough, you're thinking friction, and then you're thinking, oh, mu R, okay, so we're going to talk about that with some examples in a second. But let's say I've got something really heavy, or with a big mass, so let's say 100 kilograms here, and I try and push that on the rough surface, and I try and push that with, say, 10 newtons, right? My friction, the friction required to resist 10 newtons is not going to be the maximum friction, is it? So if we said the relationship between those two surfaces was, say, 0.2, okay, friction always opposes intended movement, or the movement itself. Okay, so that's a really important aspect. That's how you know which direction to put your friction arrow. It always opposes direction of movement. Right? Friction is never going to help you move somewhere. It's always going to act against you. So here we have our R, right? Here we have 100 G. So friction, F max, so F max equals mu R, remember? So the maximum friction this thing can generate is 0.2 times by R, which you can see is 100 G, right? So 0.2 times 100 G is 196 newtons, right? But obviously, if I actually applied 196 newtons as my friction here, the particle would be accelerating to the left. But you know friction doesn't work that way. Friction isn't a pushing force, it's a resisting force. So that's why we wouldn't say F max in this situation. Actually, in order for this, the friction that's needed is just 10 newtons, do you see? So then it's neutral, it's in equilibrium, it's not moving. But if we raise that to, say, 100 newtons, then again, friction can be maximum 196. So friction will be 100 newtons in the opposite direction, right? It'll be resisting it. And then if we applied a force of 200 newtons, well, then we would be at F max, because the maximum we can have for friction is 196. So then this thing would start to accelerate to the right, do you see? So most of your problems are always going to assume F max, because they'll be in what's called limiting equilibrium, right? So limiting equilibrium means it's on the point of moving, or the point of accelerating. Okay, so if something's at rest, if something's in limiting equilibrium, then you need to be thinking, right, F max. Or if something is accelerating or is moving, then it must be F max, because it wouldn't be moving. It wouldn't be moving unless friction was applying its maximum force, and the force pushes it beyond friction, and that's what gives it that movement. Okay. So, just to sum up there, if we hear limiting equilibrium, we're thinking F max, which is mu r, right? If we know something's moving or it's accelerating, then again, we're at F max. So pretty much we're always going to use mu r. It's just on those occasions if a question says something like, will this thing move? Or what is the friction required to stop this thing moving? Okay, so that's why you have this inequality proviso up here. Now let's get to some examples. That's what we're here for, right? So this is very similar to one of the examples you've got in your booklet. It's asking us to find A. So first I need to finish my diagram because I haven't got a normal reaction in here and I haven't got the weight of the particle. Okay, and we need to decide which way friction is going to act. Well, you can see that from the arrows, I've got 20 going left, 50 going left, so that's 70, and I've got 400 going right. So friction wants to oppose movement, right? So if this is going to the right and only 70 is going to the left, then this thing is likely to be accelerating to the right. So on my diagram, so it's getting a bit messy, on the diagram we use a double-headed arrow to say it's accelerating to the right. And if it's accelerating to the right, remember, friction always opposes movement, but I'm not going to write FR, I just go straight for mu R on my diagram. So you get 1 mark in mechanics for writing, mu R straight away. I don't really need to write friction, all right? I'm just going to write mu R in general, okay? So how do we find it? Well, how do we find A? Well, it says find A and it's telling us that mu is 0.2. So already we can write that this is 0.2 r, okay? So if we resolve up first, because we need to know what r is, so what's the forces going up? So we've got r, that's this one, and then we've got 30 newtons going up, that's that one. We've got 10 newtons going up, that's that one. And what have we got going down opposing it? So we've got minus 20 and we've got minus 50 equals mass times acceleration. The mass was 50 and the acceleration is 0 because it's not accelerating up and down. It's not bouncing up and down, isn't it? Is it? So therefore we can find what r is. R must be 30 plus 10 minus 20 minus 50. So it's going to be 30 newtons, okay? And then we need to resolve in the direction of acceleration. We always resolve in the direction of acceleration. So that's going to the right. So what's the forces going right? Well, we've got our 100, we've got our 300. What's the forces opposing it? So 50, 20, and our 0.2 r, right? And this equals mass, which is 50, times by acceleration, which is the thing we're trying to find. Now we know what r is because we just found it, so we're going to plug that in. So that's 100 plus 300 minus 50 minus 200 minus 0.2 times by 30 is 50a. If we rearrange to find a, we should get a equals 100 plus 300 minus 50 minus 20 minus 0.2 times 30, all divided by 50. So 6.48 meters per second squared. Okay, so there's example 1. Let's do example 2 then. So similar thing. This time it's saying find mu, which is like the one in your booklet. So we need an r, we need our weight, right? And then we need to decide which way friction is acting. But we already know which way friction is acting because acceleration, the double-headed arrow, is going to the left. Friction always opposes acceleration or movement. So this is our mu r here. Notice again, I'm not writing friction, I'm just putting mu r. So again, we need to know what r is, so we resolve up. Remember, I always tell your examiner which way you're resolving, and it's good for organizing it for yourself. So forces going up is r. We've also got our 40. What else is opposing it? So we've got 10, we got 30, we got 60. So there's all the forces except for the 30g. Yeah, don't want to forget about that. So nice, I'm ticking off the forces. Equals total mass times acceleration. It's not bouncing up and down. So from there we can find R. So 40 minus 10 minus 30 minus 60 minus 30 times 9.8. Whoops. Do it again. 40 minus 10 minus 30 minus 60 minus 30 times 9.8. So R is 354. I might make a mistake because I'm doing this fast, but you can always do this along with me and you get the general idea. So if we need to resolve to the left because acceleration is going left, what's our forces going left? So we've got 900, that's that one. We've got our 100, that's that one. And we've got 90 opposing it. And then we've got our total mass, which is 30, times the acceleration, which is 3. And what have I missed? That's right, I've missed friction. And friction was going to the left, so of course, mu r equals total mass times acceleration, which is 3. We know what r is, we just found it. So 900 plus 100 minus 90 minus mu times 354 is 30 times 3. Rearrange, and we should get a mu value. So I just made these numbers up, so hopefully it's something feasible. 354. So I've got a friction of 2.32, which, because I made the numbers up, that's why. But if it was in a real exam or something like that, this is why this is good. I would be thinking, oh, alarm bells, mu is not normally above 1. I'm not saying it can't be above 1. It can, but it's extremely... That's never happened before, essentially. If you get a mu above 1, something must be wrong, but I'm pretty sure we're right here. I just made up the numbers. Cool.